Hi, this is lecture 2 of group theory. So last time we said what a group is. It's a set G with a binary operation such that these three conditions hold. The first one is that there's an identity element. The second condition is that inverses exist. And the third condition is associativity. Few words on notation. From now on, when we talk about a generic group G with an operation star, we'll write A star B as A times B, or we'll just drop the multiplication symbol altogether. If we apply the group operation to A n times, then we'll usually use exponent notation and write A to the n. Let x be a set. We denote S of x to be the set of all bijections. From x to itself. Recall that a bijection is a one-to-one and onto function. We also say that one-to-one functions are injective, and onto functions, sometimes we say, are surjective. Different words for the same thing. Here's a question. Is Sx a group under the operation composition? Well, if I have two bijections, F and G, then it's easy to prove that F composed with G is also a bijection. So, composition of functions is a binary operation on the set. Next, consider this function which takes elements of x to themselves. This is a bijection, and it serves as an identity element. It's also easy to see that composition of functions is associative. Finally, for all f in S of x, since f is a bijection, F inverse is defined and also a member of S of x. So in conclusion, S of x is a group under the operation composition. Notice though, S of x may not be abelian. Take, for example, x to be the real numbers. Consider these functions. Then we have that f composed with g of x, this is equal to x plus 1 over 2. But g composed with f of x, this is equal to 1/2 x plus 1. So f composed with g is not equal to g composed with f in this case. For this example, let's look at the complex plane and the unit circle in the complex plane. Consider the point zeta 3, which is equal to e to the 2 pi I over 3. Then consider the set e to the 2 pi I k over 3 for k in the integers. Then the set contains only 3 elements. Namely, e to the 2 pi I over 3, e to the 4 pi I over 3, and 1. But with our notation from above, we can write this as zeta squared, and 1. Under multiplication, we have that 1 is the identity element. We also have that these two elements are equal to 1. So these two elements are inverses of each other. Lastly, the set inherits associativity. From the complex numbers with multiplication. So this set 1, zeta 3, and zeta 3 squared is a group under multiplication. Here's a proposition. Let G be a group. Then, if A, B, and C are in G, such that A times B is equal to A times C, or B times A is equal to C times A, then B is equal to C. Proof. Assume that A times B is equal to A times C. Then B is equal to the identity element times B, which is also equal to A inverse times A times B. By associativity, this is equal to A inverse times A times B. By hypothesis, this is equal to A inverse times A times C. We have again by associativity that this is equal to the quantity A inverse times A times C, which is equal to E times C, which is equal to C. Again, E is the identity element. The proof is similar when B times A is equal to C times A. Here's a word of caution. This doesn't hold up when B times A is equal to A times C in general. It only happens when A commutes with B or A commutes with C. Here's another proposition. Let G be a group. Then the identity element is unique. Here's the proof. Suppose that E1 and E2 are identity elements. Because they're identity elements, we have that E1 is equal to E1 times E2. But also we have that E2 is equal to E1 times E2. And by transitivity, we have that E1 is equal to E2. I left off a 2. Here's one more proposition. Let G be a group. Then inverses are unique. Here's the proof. Let G be an element of G. Suppose that G1 and G2 are inverses of G. Then G times G1 is equal to E, which is equal to G times G2. But by this proposition, we have that G1 is equal to G2.